Welcome back to the course of chemical crystallography. Today is the last lecture on this course, and today we are going to discuss about a phenomena called polymorphism. So, the point of discussion is polymorphism in molecular crystals. To start, we need to define what is polymorphism, what are they and how we should classify them. So, polymorphs are different crystalline forms of the same substance in which molecules have different three-dimensional arrangements and or different molecular conformation. So, polymorphic solids have generally different unit cell parameters, different space groups, and many times it may have different crystal systems as well. So, these different crystalline forms of same compound display various different physical properties such as different unit cell packing and resulting into different physical behavior, thermodynamic properties like different melting points, spectroscopic properties like may have different color, and then there may be interfacial and some other mechanical properties which are different for two different materials. In 1965, Macron defined polymorphs as a solid crystalline phase of a given compound resulting from the possibility of at least two different arrangements of molecules of compound in the solid state, which actually means that a particular compound, when you try to crystallize it from different methods using different solvents or different methods like slow evaporation, rapid evaporation, solvent drop grinding method or vapor diffusion method, if you end up getting two crystalline states which have different powder X-ray diffraction pattern, then we call them as polymorphs. So, physical properties of polymorphs differ in various polymorphs. The molar volume and density may be different. The refractive and index, melting point and sublimation temperatures may be different. The enthalpies of those solid crystalline forms will be different. The solubility of those different crystal structures in a given solvent may be different, and of course, some vibrational transitions like infrared absorption spectroscopy and Raman spectra may be different for those different crystal structures. In addition, there may be differences in resolution rate, differences in solubilities, hardness, compactability, handling procedure, flow and blending methods. Like one polymorph may be free flowing, one polymorph may be sticky. These are different physical properties that are seen to be different in case of different polymorphs. An amorphous form is not a polymorph because an amorphous form does not represent a single phase. It may be a mixture of two or three more different non-crystalline phases, and hence it cannot be called as a polymorph. So, a clathrate or a hydrate can be called a polymorph. Many pharmaceutical solids exist in amorphous forms, and because of their distinctive properties, they are sometimes regarded as a polymorph in pharmaceutical industry, but unlike true polymorphs, an amorphous form is not a single type of crystal and not considered as a polymorph in general. So, when we try to claim that we have generated a new polymorph, we first include the name or structure of the chemical compound, apply a standard convention to designate and name the polymorphic forms, and distinguish it from other polymorphs and pseudo-polymorphic forms already in the literature using some physical methods, and incorporate comparison and characterization data for the new crystalline form that has been identified. So, suppose we have a particular compound with hydrochloride HCl as a co-former, a compound one can crystallize with water molecule, and a compound can crystallize with both HCl and water. So, then this becomes a new compound and not a polymorph. So, polymorphs generation is a very important phenomena in pharmaceutical industry and in general in crystal engineering community. So, there are few theories that we need to understand behind the formation of polymorphs. The specific crystal lattices and number of lattices of a polymorphic polymorph are not known easily. The specific crystal lattices and number of lattices of a polymorph are not easily predictable. Even if one could predict that polymorphs exist, there is no general teaching or suggestion in the literature that shows how one can predict to make a particular polymorph. And no teaching or suggestion exists in the literature to identify and to appreciate the properties and characteristics of a particular polymorph prior to it being identified. So, what we are trying to indicate is that just by looking at a molecule, a chemical sketch, it is not possible to predict whether it will have more than one crystalline forms. If it can have more than one crystalline forms, then how those forms can be generated. Nowadays, there are some crystallographic software, some packages where the computational tools are used to predict different polymorphs, but it is not always experimentally achievable. A method of making a new polymorph is not known until it has been identified, and the new crystalline form has a different properties over the earlier known forms. Until and unless somebody does an experiment and arrives at a new particular crystalline form, we cannot a priori predict that this particular form will be found or it will not be formed. It may not be obvious and not possible to predict few things like how many different crystal forms can be prepared from a particular compound, how to prepare any as yet unknown crystal forms, and the properties of any unknown crystal forms. So, these predictions are not yet possible. Therefore, a new crystal forms are potentially patentable entity. So, when we try to characterize these crystalline forms, we use different methods. The first and foremost important method is powder X-ray diffraction. Then if we can grow a single crystal, one can do single crystal X-ray diffraction to elucidate the structure. We can do IR or Raman spectroscopy, solid state NMR, and also we can identify polymorphs by morphology, but it can lead to some difficulty. So, beyond having a diverse collection of characterization data, the data for a novel polymorph should be analyzed to demonstrate how it distinguishes over other disclosures, including the compound per se and more particularly over the other polymorphic forms. So, we need to establish the superiority of this particular form to be able to use it in lieu of the original form. In addition, the characterization data that evidences unexpected or superior properties over properties of the original compound and other polymorphic forms could make a stronger or reliable case. So, there are different types of polymorphs that has been characterized in the literature. The first type of characterization is first type of classification is conformational polymorphs, where the molecule changes conformation and crystallizes as a different molecule, different structure. Packing polymorphs, where the compound crystallizes in different three-dimensional arrangement but maintains the conformation of the molecule unchanged. Solvatomorphs or solvates or pseudopolymorphs are crystal structures of the same compound which involves the solvate. And lastly, the concomitant polymorphs, where two or more crystalline forms may grow in the same crystallization setup under the same conditions. So, these are like twins. These are growing from same solvent under the same temperature and pressure and same conditions of rate of evaporation. So, now the question is, if we have these two compounds in crystals, are they polymorphs? You can see that these two compounds are geometrical isomers. Here this C double bond N is having a trans arrangement with the nitro group and the methyl group. Here the nitro group and the methyl group under phenyl ring are in the cis arrangement. So, these two are not polymorphs, rather these two are different compounds. So, two polymorphs should not have any difference in their bonding features. So, now we need to understand the thermodynamics of polymorphic forms of molecular crystals. We know the Gibbs phase rule as stated as F equal to C minus P plus 2, where F is the number of degrees of freedom of the system, C the number of components, and P the number of phases. And we define a phase as any homogeneous and physically distinct part of a system which is separated from other parts of the system by definite bounding surfaces. So, by this definition, for any substance there is one gaseous phase and one liquid phase, since this must be physically and chemically homogeneous, and the solid state may have more than one phases existing together. So, each crystalline form constitutes an individual phase, for example, the different forms of ice. A mixture of two polymorphs contains two solid phases, but a homogeneous solid solution or an alloy of two totally miscible metals is only one phase. The number of component is the minimum number of independent species required to define the composition of all the phases, and number of degrees of freedom is the number of variables that are temperature, pressure, concentration that must be fixed in order to define the condition of the system at equilibrium. So, for polymorphic systems of a particular material, we are interested in the relationship between polymorphs of one component. A maximum of 3 polymorphs can coexist in equilibrium in an invariant system, and since the system cannot have negative number of degrees of freedom, so this will also correspond to a triple point. The number of degrees of freedom is the number of variable factors such as temperature, pressure, and concentration, and that must be fixed. So, a one component system is one phase, say a gas, would have 2 degrees of freedom, as we know. A one component system in a two phase equilibrium, that is liquid and gas, would have 1 degree of freedom, that is a phase boundary, and a one component system with 3 phases would have no degrees of freedom, that is called a triple point. So, here I would like to just remind you about the phase diagram of water. To explain this, let me draw the phase diagram of water here. In phase diagram of water, we plot pressure in the y axis, absolute temperature in x axis, and we know that for water we have a negative slope for solid liquid interface, that is this line has a negative slope and this is the vapor. So, solid, liquid and vapor. So, if we are located somewhere at in any one phase region, we have simultaneously 2 degrees of freedom. When we are sitting on one particular line, say for example solid liquid phase boundary, we have only 1 degree of freedom. So, if we change one component, either temperature or pressure, simultaneously the other one also changes and the equilibrium is maintained. And when the 3 phases coexist, this point is called the triple point, where at that point we cannot change anything without disturbing the equilibrium of 3 phases. So, the relative stability of the two polymorphs depend on their energies, and always the most stable form is the one which has the lowest energy. Those forms which are less stable will be energetically driven to transform into the most stable form. So, kinetic factors may prevent such transformation. So, as we are dealing with solids, the differences in the volume between polymorphs are small fractions of volumes of the solid themselves. So, we can then neglect the volume and pressure changes with energy. So, under constant volume and temperature and pressure, the free energy of the solid may be represented by Helmholtz relationship as shown here, A equal to E minus Ts. So, where E is the internal energy and T is the absolute temperature and S is the entropy of the particular solid form. If we try to plot the energy versus temperature for two different polymorphs, what we can see is that suppose this one is the polymorph 1 and this one is for the polymorph 2. So, the energy of polymorph 1 is lower than energy of polymorph 2 at a very low temperature, and when we are increasing the temperature for polymorph 1, at one point we see that the Helmholtz free energy, that is A value for the form 2, meets the A value of form 1 at this particular junction, and beyond this point the A value for form 2 is lower than the form 1. So, if we are heating form 1 at this particular transition temperature, form 1 should get converted to form 2 and it should exist at higher temperature. So, here we are trying to show the Gibbs free energy versus temperature plot, where it is G equal to H minus Ts, and what we have here is the energy versus temperature diagram of a diamorphic system. So, what we have here is the form 1, which is the most stable form at low temperature. This is the form 2 and that is the liquid phase of that particular compound. So, now here what we see is that at a particular temperature, while heating, Gibbs energies of the two phases become equal, and beyond that temperature the Gibbs energy of phase 2 is lower compared to Gibbs energy of phase 1. So, what happens in this case is, if we are heating form 1, beyond this temperature form 1 gets converted to form 2, and then when that form 2 reaches this particular point where it meets the G of liquid, form 2 melts. So, if we try to see this phenomena using differential scanning calorimetry, what should we see? Suppose we are plotting the heat flow versus temperature of form 1. So, on heating, form 1 at some temperature gets converted from form 1 to form 2, and what we have is the form 2 having higher energy compared to form 1. So, form 1 will absorb energy and get converted to form 2. So, if we plot the endothermic transformations up, then this transformation of form 1 to form 2 is an endothermic transformation, it absorbs heat. So, we should see a peak. So, before the peak it is form 1, after the peak it is form 2, and then when we are heating, this form 2 meets the G line for the liquid at much higher temperature, and then at that temperature it melts. As we know, melting is an exothermic process. As we know, the melting is an endothermic process. Once again, form 2 takes up more heat and goes to the higher energy level for the liquid. So, once again we have another endothermic peak indicating the melting. So, on this side, the right hand side, we have the liquid. So, this peak indicates melting. Now, if we start cooling this molten liquid, what should happen? So, when we start cooling this liquid, at that point this liquid is being cooled from here backwards. That means, again when the liquid crosses the G curve for the phase 2, the form 2 will be crystallized, and crystallization is exothermic process. So, it will be a solidification peak like that. from liquid to form 2, and then when we are further cooling, once again at that particular temperature, beyond that when we go lower, form 1 is more stable compared to form 2. So, again transformation from form 2 to form 1 will take place. So, if such a thing happens that one phase can be converted to the other and it can reversibly come back, then this particular system is called the enantiotropic system. But now you remember, if we had done the experiment by starting with form 2, if a form 2 is formed during an experimental process by some means which is thermodynamically unstable form. So, if we do the experiment with the corresponding thermodynamically unstable form, what should happen if we do the DSC analysis of the same thing? So, we again write heat flow endo up and the temperature on x axis. So, now I am heating a phase form 2 which is thermodynamically unstable, but then this form 2 continues to remain as form 2 at this particular junction temperature where there should have been a change of form 1 to 2, but then since it is already 2, there is no change. So, this particular form straight away goes and melts at the melting point of form 1. So, this is form 2 and this is liquid. But now, when we try to cool this liquid, what should happen is that the liquid is solidified at the solidification temperature at that point, and then when we are further cooling it, when again the phase form 2 is crossing this particular temperature, it should get converted to form 1 and we end up getting form 1. So, we started with form 2, we ended up getting form 1 after the first cycle. So, now it indicates that we have got the thermodynamically stable phase from the thermodynamically unstable phase which was somehow formed during the experimental process. So, this type of system is called the enantiotropic systems. The other possibility of a similar diamorphic system can be shown like this, where the energies of form 1, 2 and the liquid phase are shown here, the corresponding H and G's are shown, and what we see is the plots for G for 1 and 2 do not intersect at any point before their melting points. So, what happens if we do a DSC of such a system? So, we again plot the heat flow in y axis with endo up and temperature in the x axis. So, if we have started with form 1, which is the thermodynamically stable form, on heating from a low temperature in this direction, form 1 does not get converted to form 2 at any point because the G line for form 1 is not meeting the G line of form 2 at any point. So, form 1 melts at this particular temperature which is the melting point of form 1. So, what happens when we do simple DSC? Form 1 goes and straight away melts at its melting point. Melting is endothermic process. So, now if we again try to solidify this liquid is cooled from a higher temperature at the melting point, again the solid form 1 should form from the liquid, and the DSC trace should be very similar to what I have drawn here. This peak indicates crystallization. But if we had done this experiment with form 2, what we could have seen? Form 2, you remember, is thermodynamically unstable phase, and it has a melting point which is lower than that of the form 1. So, if we are heating this sample from room temperature, at its melting point it will first melt. So, in terms of energy on melting, this form 2 goes from here to there by absorbing that much energy, but then at that particular temperature form 1 has a lower energy. So, immediately the molten liquid will resolidify back to form 1. So, this molten liquid will immediately solidify to give you form 1 and will generate an exothermic peak like this, which will then indicate that form 2 is melted or molten, and phase transition has taken place to form 1. And then when we heat this form 1 further, it goes and melts. Melting of form 1, and this is melting of form 2. So, once again, if we solidly cool this form 1, we would get the crystallization peak, and it will crystallize as form 1 and not as form 2. So, when we see some thermal behavior like this, we term this particular system as monotropic diamorphic crystalline system. So, today in this part of this lecture on polymorphism, we have learnt about the definition of polymorphs, classification of polymorphs in terms of their crystal structures, and also we have learnt what are monotropic and enantiotropic crystal phases in polymorphs, and we have understood how these different types of polymorphs will behave in the differential scaling calorimetric experiments. So, what it indicates that if we have generated a particular polymorph, or if we have generated a large number of polymorphs of a particular compound, then we must do a careful differential scaling calorimetric experiment to identify whether it is a monotropic system or an enantiotropic system. So, in the next lecture we will continue this discussion.